Welcome to another great CalBasic demonstration. This is part 8 of the tutorials for the 16F171 chip family. Hello, my name is Venn. I'm a co-developer of Great CalBasic and I'm walking you through these tutorials. So let's get into the PowerPoint to recap where we are. We're looking at serial values being displayed on a terminal. So we're going to make the microcontroller talk to a PC into a terminal application. Very useful, not only in the context of these tutorials, but for debugging and communications. So what am I using? I'm using the microchip low pin count demo board, shown on the left in green, but you can make your own, and we've given you a layout for that by colleague and friend, Chris Roper. So let's have a quick look and recap what serial output is. It's actually, you're going to be using the built-in UART, or universal synchronous asynchronous receiver and transmitter, that's built into the PIC. And it will communicate over the serial communications line to a terminal on a personal computer or PC. This baseline for this tutorial is everything we've done before, plus a little connector that we'll have a look at in a moment. So what's the layout we're using? Well, we're going to connect ground or 0 volts to our board, and we're going to take out from the chip on port C4 the transmit line, TX, or TX1 if it's got more than one transmission. And that's going to be connected to these little USB TTL connectors, and we're going to connect it to the RX, the receive on here, and 0 volts, or ground. So we've got a common ground, common 0, and the TX is connected to the RX on here. And that is all we have to do to make these things communicate. But within the chip, we need to set what's called the PPS, the peripheral pin select. It is a crucial step to configure the microcontroller to give you the transmission or the USART capability on specific ports. PPS is a very configurable and highly flexible technology that allows you to tailor the configuration of a microcontroller for your own use. Today, we need to set the TX, the transmission, or TX1 using PPS. We have no option. It is not pre-configured for you. We have a tool that's called for peripheral pin select, called PPS, and you can access that via PIC info, which we've seen before, or we're going to access it directly from the IDE, which is what I'm going to do today. And so the key thing today is the same process we've seen before, but I'm going to add into it the send some values of the ADC and direction of travel to the serial port. It's very simple. We have a few commands to add and it will start communicating. So let's look at the example code, the example demonstration, review the results, and have some fun. So let me go to my desktop. GCStudio, chip range demonstrations, and get into the IDE. All right, I'm going to open up the filter, put the filter on, GCB, and apply the filter. I put a comma in the filter, that won't work. Apply the filter. Demonstration 1.gcb. Apply the filter, done it. Take 100 reversible LEDs. Great. Shut the Explorer. Let's zoom in on what we've got. Well, we've got the standard header that we've had always before. We've got 16F126, and we've got some more code which we haven't seen before. Well, this is the PPS code. I'm going to delete this, okay, so we can recreate it. But we just need to do this quite early on in our process. So press F4 to bring up all the tools we have available. PPS tool. This is user tool, and open it up. Here is the user interface PPS tool. You select chips at the top left, pre-selected, and you can choose inputs or the outputs. Well, I want to transmit, I want it on TX1. I select it, and I'm going to connect it to C4, RC4, which is done, and add that into my list of configurations. And now there's a green little icon at the bottom to tell me which port it is. Now I know to connect my TX connection to here. I'm going to copy that. It copies it to the cut and paste buffer. If I now go back into the IDE, let me just minimize that. I can now paste it into here by using the cut and paste buffer. And now I've got the commands that I require. Let me just recap. I have a subroutine, and in there it has one instruction. Connect RC4 PPS to a number, and that number equates to the transmit line. And what is important is that these numbers vary between chips. You cannot copy the configuration or PPS configuration between chips. It's not possible. And we do it. Look, here's a reminder of the chip that we did it with, and then there's what's called a startup line. Hash startup. Call this routine early in the initialization process. And it does that to ensure that it is initialized early so that you can use it as early as possible. Let me minimize that because we've done that. I've added in my documentation, I've got port C4, the TX1. Same constants as before, but I've got a new set. And this is very simple. It says hash define USART baud rate 9600 and USTX blocking. Two constants. One sets up the communication speed, and the other one just tells it to ensure that the buffer is empty before it sends out the next piece of information. So TX blocking essentially ensures a clean transmission. Those are the two things that you need to do, plus PPS, of course. Same program as yesterday. And then we have new instructions. H serial print commands, there's quite a few of them. That you can put carriage returns out, you can print strings, you can print the chip name, speeds, numbers, etc., etc. And it will send anything with H serial print to our communications port that we've defined. And in our program, I'm doing pretty similar stuff. I'm going on from yesterday. We know that the direction will be set to LED right or LED left. So if it's on the right hand side, send out a right hand arrow and R, else send it out a right hand arrow and a left. Send a tab and then print out the value of the delay that we're currently using. And that is the program. So we've added in, recap, PPS, two constants to set up the communication speed, and then these strings or commands with strings and values to be displayed. And I can make the hex and it will compile quite successfully, but I need to open up a terminal on my computer to make this communicate. So I'm going to press F4 into the tool list, terminal. And there's a serial terminal included within the software, and it's now showing on the screen. Let me bring in another item. Let me bring in the lab, and we can see it's where we left it yesterday. Let me program it by pushing the hex and flash, and it will program it. The terminal at the moment is not connected. It's purely opened up the session for you. Now, if I Look at the application. I need to select the communications port that I'm using. Well, I know that it's on COM10. Connect. And now we can see values that relate to the strings that we saw earlier on. If we look at our code, we can see we've got ampersand, greater with an R. And if I change the direction, that would become less than L. And it does. If I change the potentiometer, the values will increase up to the top of our range, or to the bottom actually. The screen's a long way away from me. And we can see we have now got communications. If I reset the programmer and take the voltage off it for a second, then reapply it, we will see the header string appear in our terminal. Great Cal Basic on a 16F17126 at 32 megahertz. So we can send values backwards and forwards. We can interact with the microcontroller through the serial port. We can do inputs and outputs, all through this very similar commands of H serial, print, inputs, etc. And so what we want to do today is really connect this microcontroller to the outside world. And I think we've done that rather successfully, because now I can change the port and I can see the values on the screen. I have serial communication between the two devices. That's the microcontroller and the PIC. That's all I wanted to show today, but we have seen PPS tool as well. So we are diverging on the next tutorial. We're going to be looking at timers, timer overflowing. We're still going to be using the LEDs, of course, but we're going to use different methods. We're not going to be using a weight, a calculated weight. We're actually going to be using interrupts and the overflow engines and the overflow of our timers to change our rate of the pulsing of the LEDs. And with that, we'll call it a wrap.